current carrying loop produces the torque force when it is placed in the magnetic field like this. The placement, the loop carrying current can have different orientations in the magnetic field. The direction of magnetic field is like this, is on the plane, in the straight line like this, plane of the board. This loop we can have different orientation with respect to the direction of magnetic field. This is one of the orientations I explained. This orientation produces the torque force M into B. That is the cross product of two vectors. Final equation for the torque by this current carrying loop is M into B. Cross product of two vectors. This vector is magnetic dipole moment, which is perpendicular to the plane like this. Direction of magnetic momentum, outward force. M direction is this. B direction is this. They are perpendicular in this case. Produces torque force. For this alignment, what are the other orientations or the alignments of the loop? This is what the rectangular loop I am taking. This is this alignment is similar to like this. This plane of the loop, it is exactly on the plane of the board. This is same. This current in the loop produces the torque like this. The different orientations I said. If you, that is rotation about the axis. If you rotate this loop through 90 degree, what is the alignment you get? Rotation means rotate about the axis like this. The alignment exactly 90 degree. Now the loop alignment is like this. What is the alignment? The plane is like this. The plane is perpendicular to the board like this. But the current direction remains same. Current direction in the loop remains same. That is what I have written the diagram here. This is the original one, initial one. When it is rotated through 90 degree, that is the actual alignment or orientation. But the drawing is like this. This space is this. After rotation, it becomes like this. That is what we get now. Rotation, AD, rotating through what is that? You get like this. This side is this side, and this side is this side. Upside is this, lower side is this. Rotation, and the direction of the current. Direction of current is same direction. It is alignment. With this alignment, direction is showing like this. And one more orientation. If this is a orientation, and one more orientation, one more alignment of the loop, it is further rotated to 180 degree, another 90 degree. There one more 90 degree rotation. Now the alignment is there, again plane. This plane, what is that? Interchange these sides. Look at this. Sides are interchanged, but the direction of the current in the loop remains same. Sides are interchanged, resulting what is that? Showing the current direction. Looks like it is reversed, but the current direction in the loop remains same. It is due to rotation changes like this. Initially it is rotation like this and rotation like this. Another 90 degree. This is rotation alignment. And and one more rotation, that is one more alignment. With this, it is further rotated to one more 90 degree, another 90 degree, total is 270 degree. From here to here, rotating through 90 degree, from here to here, rotating through another 90 degree, from here to here, rotating to another 90 degree, that is alignment. Look at this current changes, direction of the current changes, but current in the loop remains same. Sides are changing. Let us do one more rotation, one more like this now, 70 to 70. One more rotation, one more 90 degree, like this you will get back the same. With this every 90 degree, when you do the rotation, we get different alignment of the loop with respect to direction of magnetic field. Direction of magnetic field. In these different orientations, will they produce torque force? This alignment and this alignment produces torque force. But this alignment and this alignment will not produce torque force. Alignment. That is, do the calculation. The force on every, what is that? On every line, that is side is, that is F. Here 0, 0, here F is there. Because when it is perpendicular like this in the perpendicular direction, and this line is perpendicular to magnetic field, this line is perpendicular to magnetic field, all lines, that is, all lines are perpendicular to magnetic field. And calculate the force exerted at this conductor, the amount of force is the same equation, but the direction is very important. Here are two equal forces. What is the direction? Direction using palm rule. That is the one, palm rule, wording like this. Here with this current direction, this is the direction of the current, facing, force upward. Here direction of the current like this, upward force perpendicular to the line. Here the direction of the current, what is that? That is what is direction. Direction, this is the one. Outward force perpendicular to the line. Here again, what is the direction? Perpendicular to the line, upward. Look, these forces, what's the direction we have found out. Between these 2 points, perpendicular line, the force is in the direction, in this direction, same line. The forces are in the same line with these 2 conductors. The forces are in the same line with these 2 conductors, but in opposite direction. But in opposite direction, the forces with these 2 lines, with these 2 conductors, the same line, opposite direction. The forces due to these conductors on the same line, opposite direction. Same forces, same line, opposite direction, cancel. Same forces, same line, opposite direction, cancel. Net force by all the forces, because on all conductors the force is exerted, but the net force is 0. If the net force is means torque is 0. Torque is a result of net force by all the conductors. But in this alignment, it is rotated, left becomes right, right becomes left, and the current direction changes. Do the same calculation for these 2 in the same, that is same line, a magnetic field and the lines are same. No forces at these conductors, but here forces are exerted because perpendicular. The forces are exerted similar to this, but the forces are in the opposite direction because the current direction reverses. Here the current direction reverses, the forces also reverses. Same couple of forces. Here inward, here outward. Difference here. Here it is inward, it is outward. Here outward it is inward like this. So this will give what is that the current in this will rotate in the anti-clockwise direction. The torque rotation in the anti-clockwise direction, here rotation in the clockwise direction. The alignment, current direction remains same, it is rotating through this. And similar to this, 270 degree. From here to here, 190, 270 degree like this. When you do so, the current directions now like this. Current directions exactly reverse in these cases. Direction of corrections by view is different, but current direction remains the same, but rotation through 270 degree. If you find the directions of the forces on each current, on each conductor, like this, so that is what you get, the current direction like this. Here the direction what is that? Inward forces. Now look this upward, this is inward direction, the current, inward forces. Here inward forces, here inward forces, here inward forces. Using this form, it is the forces exerted due to these conductors in the opposite direction, same line towards each other, get cancelled. Same magnitude. Here the forces are same at each conductor in the opposite direction towards each other on the same line. It is again get cancelled. Here outward, here inward. Net force resulting in torque is 0. The net force is 0, torque is 0. Now it is understood. When the loop is in perpendicular direction, notice this 90 degree or 270 degree rotated, that loop will not produce torque force. Torque force is produced only when it is in the plane like this and the plane like this. Rotation is, it is clockwise direction, is anti-clockwise direction. Now this is what you understood. Using this torque, the loop can produce a torque only with the two alignments. This alignment and this is alignment gives clockwise direction, this is alignment with anti-clockwise direction of the current. So that is what you understood using force. Using also what is the direction of the magnetic field, that is magnetic field and magnetic dipole moment M. So with this alignment I said direction of the M is this, perpendicular to magnetic field. When this is the alignment, so this is the direction of the magnetic momentum. Magnetic momentum and the magnetic field are in the same direction, 0. That is M into B, theta is 0. Angle between M and B with this alignment, that is the direction of the M. M direction and both magnetic field directions are same, 0. In other way, this is with this direction, magnetic momentum is like this, perpendicular. So it reverses the rotation. In this direction, what is that? Magnetic momentum, that is the direction is like this. Magnetic field is like this, magnetic momentum is like this. Magnetic momentum is like this, 180 degree. So angle between M and B is 180 degree. Sine that 180 is also 0. These orientations will not produce torque. These orientations produce torque. This current produces clockwise direction. This current produces anti-clockwise direction of the current. So this is the one we use, or in the application of conversion of electric current into mechanical energy. This is a loop I am taking. For a continuous flow of current in the loop should be connected with a source of electric current. There are two sources of electric current, DC current and AC current. Direct current, alternate current. Now if you do so, we see that there are two types of circuits. This is a circuit, a rotating circuit. It is a moving circuit, rotating circuit. Another circuit, stationary circuit. This is rotating circuit, this is stationary circuit. There is source applied. Here also rotating circuit and stationary circuit. What is this DC motor? DC motor is designed. What is the design? It designed so that this loop always rotate in only one direction, either clockwise direction or anti-clockwise, continuous rotation. What is the design and make of the DC motor? This is the design and make. Very important here. Here the source is applied to two carbon brushes. They are fixed carbon brushes, very good conductors. Carbon made of nanocarbon, connected like this. Always plus, always minus. This carbon brush, and these are connected to what is that? That is a spherical shape. That is sphere. It is called splitting commutator. Split in between, so that they should not be touched with disease of our hemisphere. And this is a spherical shape, always both together spherical of hemisphere. They are, while rotating, what is that? This is connected. This end is connected to this commutator. This end is connected to this commutator. While the loop is rotating, it can rotate about its axis. This also rotates. Since it is fixed to this, it is fixed to this. Rotation. But these two are fixed. While it is rotating, this sphere or splitting commutators both together, what is it? Rotating. For rotating, this surface and this surface slide over. Always touch, slide over. Should be in touch because no current should not be, no gap, should be touched. Slide over produces, of course, what is that? Friction between this surface and fixed and rotating. So it is rotating like this, sphere with a split like this. This surface and this surface are in touch and use friction. This friction is reduced as much as possible because we are using carbon brush or ideal lubricant. That is the reason why you are using carbon brush. There are two important points. Carbon is a very good conductor and this carbon is a highly lubricant. During rotation, it will not wear out, not produces much friction. That is what we need, material. Now when you apply current plus and minus, direction of the current passing through this, like this, and the current passing through this is minus. So with this current it rotates. This current can produce magnetic force, that is rotational or torque force to rotate. There is enough force produces to rotate through 180 degree off of the rotation. When the current flows, it will be rotated through 180 degree, 90 and again 90. This alignment becomes this alignment with this rotation. When this loop is rotated, this also rotated. After 180 rotation to 180 degree, what was here comes here. What was here, it comes to the point. Look at that. It was here, it will come to this position after the rotation. Now it will change what is the position, but the current direction, what is that? Current direction is not like this with 180 degree, because this will change. What is that? This positive becomes negative, negative becomes positive. With 180 degree rotation, what the current originally here, direction like this, after the rotation, what is that? The current in the circuit reverses. But you see that our view That is where what you are giving the current direction in the circuit remains same. It looks like the previous one only. It is because of reversing of the current in the this device will reverse for every 180 degree. It reverses the polarity. Plus becomes minus, minus becomes plus. That is why current direction in the loop it looks same while you are giving rotation. If this is the direction, what is that? Clockwise rotation. Even after this, one more clockwise. Right? It's clockwise only, no like this. For every 180 degree, current in the loop reverses. And with 180 it is view remains same. Again clockwise, again clockwise. Yeah, 180 degree clockwise, clockwise. So this produces a continuous clockwise direction. So it is rotated continuously in the clockwise direction for every 180 degree like this. So DC source, that is electric current, changes into mechanical energy. You see that the continuous rotation of the torque, that is called as armature. And the amount of torque force we need, because this change of current, what is that? Changing current into mechanical energy. The mechanical energy in the form of rotational energy, which you change into for lifting of water by devising pump set, or changing into a linear, that is rotational motion, into linear motion by devising electric motor, or by running the machines, light machines and heavy machines, rotational changes, releasing this power, producing mechanical energy. That is the application we conduct. To increase the magnitude of the force, torque force, to increase the mechanical energy from what the source you are using, here too it depends on the amount of energy output I am talking about. This is the input, current input, but we can increase the output energy. Look at this, this output energy depends on all these factors. Current strength in the conductor, that is the current strength what you are applying, and the area cross section of the conductor, and B is the amount of, by increasing the external magnetic field. And one more, we have only one wire, one turn is there, one turn produces this amount. But if you can move so many turns, you have multiple turns. The conductors, what is that? By insulation, what is that? Your turns, many number of turns. For every turn, it multiplies. Thousands of turns. It becomes a, what is that? More amount of kinetic energy. So to increase the output, you have to increase I, you have to increase B, but mainly it is increasing the number of turns in the coil. That is called as armature. It is rotates about the axis, produces mechanical rotation. So this is a device or design, the DC device or design which produces continuously electric energy into mechanical energy. This is DC motor. Then what is AC motor? The design is different, because AC means it is a plus means plus minus. This always plus, this is always minus. DC current. But in AC current, here the carbon brushes are there. Carbon brushes are there. It will interchange. One time plus, other time minus. Interchange plus, minus, minus, plus. Plus, minus, minus, plus in interchanging current. If that is the case, what should be the design of this armature or this loop? This. Here, device is like this, is connected to a ring like this, a cylindrical ring like this, and this is connected to one more cylindrical ring like this. Look at this, these two rings are separated like this. While it is rotating about its axis, this will rotate about its axis, this will rotate about its axis, but in the same line, not like this. This rotation, what is that? This rotation in touch with this carbon brushes are fixed. That is again stationary circuit, this is rotating circuit. So this what it will, while rotating, it will glide, what is that, slide over the surface between the this slide over the surface, just slide over the surface like this, but always in touch, carbon brushes only, because to minimize the lubrication. So when it is rotating, when it is rotated to 180 degree, so this becomes, what is that, this rotated to 180 degree, here the terminal remains same, but with every rotation of 180 degree, it will change current, plus becomes minus, minus becomes plus. When through 180 degree, this it comes here, no, this comes here, when it comes here it becomes minus, that is the direction becomes minus, not the same direction. This device so that terminal remains same, but the current reverses by the AC source. Here terminals are, what is that, changes, current direction remains same, current reverses by the terminal change, because the design is different. In AC motors, we have this kind of design, that is slip rings. So it is rotating, there are two rings are there in the axis like this. So while rotating along the axis, we have this, they separately rotating these slip rings. Terminal remains same, but current reverses by AC current. Here terminal remains same, current reverses by splitting commutator. That is the design. So this produces, what is that, AC source current into mechanical energy. Continuous again. The current remains, what is that, this direction, what is the view, it remains same at every rotation, 80 degree, 180 degree. Therefore, it is always continuous rotation in clockwise direction. Continuous rotation is continuous mechanization. That is what we design. So in this, we produce, what is that, mechanical energy by using electric energy. We produce mechanical energy by using electric energy. The same device, let us reverse the process. That is, conversion is how to get mechanical energy using electric energy. Let us reverse the process and see. What is the process? Here, rotate this. In the magnetic field, what is that? Let us rotate this. Let us rotate this, what we get. Apply mechanical energy. Mechanical energy we can produce. You can see in the nature, in the form of, what is that? Flow of water, a blow of window, or converting heat into mechanical energy by turbines. So you can produce mechanical energy. It is source available. If you apply this mechanical energy to this armature or the current like this, it will rotate this. If it is rotated, then it is the electric energy is generated. Reverse process. Mechanical energy into electric energy. Same. That is DC current produces by this device. By this device we get AC current. Same device. When you apply mechanical energy, electric current. When you apply mechanical energy, electric current. Reverse is current into mechanical energy. So usually at production of power at a large amount, we go for this AC production, this device at the production center, where the electric power generators are there, hydroelectric power generators or wind energy or thermal energy production. We go for what is the production of AC. This is a very good source of energy. This is what the principle or the principle and the device what you design to get a continuous conversion of electric energy into mechanical energy and mechanical energy into continuous energy. You can produce both DC current as well as AC current. With this you are completed with this. Thank you very much.